And so we're gonna pick up where we left off last time on Wednesday. And who remembers what hormones we've talked about so far? What hormone products have we talked about? LH and FSH. I heard progesterone. What else? Prostaglandin. Good. Anything else? I don't know that I'm hearing anything else. What have we not talked about yet? There's a big one. GnRH, good. Yeah, we're going to talk about GnRH today. And there's one other one that we talked about possibly didn't talk about on Wednesday. Oxytocin. Good. So that's actually where we're going to start today. We're going to start by talking about oxytocin. And again, another product that we can use on both the human and the animal side. So on the animal side, we tend to give true oxytocin, right? Anybody ever given oxytocin, like in a dairy setting or in a sow farm? Yeah, a few of you. Good. So now we're going to move on to those GnRHs. So on Wednesday, we talked about what an analog is. Anybody want to remind me what those analogs are? Nobody? Yeah, very good. They're a product that's very similar in structure to the natural hormone, but tweaked just a little bit, okay? So almost all of our GnRHs are, well, actually all of our GnRHs are going to be a form of an analog, okay? So they will bind to those GnRH receptors. They're not quite the same structurally, but they're just enough different that they can still bind to the receptor, but they have a longer half-life so they can live in the blood. So we have three categories in our GnRHs. We have the analogs, which like we just said, have the same effect as that native GnRH hormone, but they're just a little bit different structurally. We have a GnRH antagonist or GnRH agonist. Okay? We have three categories to our GnRHs. Okay, so this should look familiar to the handout that you guys have. So we'll kind of walk through this now, and we're going to talk about the actual mechanisms of action that each of these GnRHs have on the receptors. Okay, so here we have our normal GnRH receptor, where we have our GnRH binding and fitting in there. We remember back to a few weeks ago, Dr. Fike talked about these receptors like a lock and key. So it may fit in there, but it may not work. It may fit and turn the key, okay? So we'll kind of think about those, or these here as lock and keys, okay? So that's our natural native GnRH. And then we have our GnRH agonists, okay? And those are going to cause flares initially of that LH and FSH. And then they're going to and then after that, they're going to downregulate and kind of cause some desensitization. All right, now we're going to move into talking about immunocastration. And I think that this is an area that's really cool. Something that's not used as much in the United States, but it's heavily used in Europe. And something that could be used here in the United States for helping control some of like our wild boar populations, or as consumer views and preferences about castration change. This might become a lot more popular in the US, okay? So it's an alternative to that surgical castration. So normally when we think of castration, it's the actual removal of testes from the body. This is a way that we can actually immunize the animal against some of these reproductive hormones to prevent cyclicity. So essentially it arrests the function of the testes or shuts down the function of those testes. Okay, so the way that this works and the way that we use it is a tool that acts on the immune system to suppress gonadal function. Okay, so it builds antibodies against GnRH to shut down GnRH production and thus shut down testicular function. Okay, because we need GnRH for LH and FSH, and we need FSH and LH in the testes for testicle function, right? So all sounds familiar? Okay, so you guys can probably, I pushed the right button. You guys can probably see down here. So these would be some bulbourethral glands from a non-treated male. These are some from a treated male. Again, full normal testicular development of a non-treated male, essentially zero testicular development and function in that male who was treated with the infrarest. Okay, so why do we castrate boars? Who knows why we castrate boars? Yeah, meat quality is a lot better. So essentially, what is affecting meat quality in our boars is what we call boar taint. Okay, so that is one of those things that makes a boar at the time of harvest a lot less desirable. And why we actually harvest and consume our barrows and our gilts is because boar taint. Has anybody ever had or been around a boar like post-slaughter, post-harvest? Yeah, it's gross. Like it's a nasty smell, and it's like the meat even looks funny. So boar taint is really bad. We definitely do not want, if we're in an industry where we want to feed people, we really don't want to feed people a bad product, right? So we're feeding people more meat, so that's probably not going to make them want to eat more pork, right? So that is why we castrate our boars. So where that boar taint is actually coming from is from right here, this androsteny and scadal. All right, and where it's produced, so again, just look familiar. The hypothalamus releases GnRH, LH comes back to the testes, and the testes in the boar create these two hormones, and then two of the steroid hormones that are produced in the boar in heavy quantities that then get stored in the liver, and then from the liver, it gets deposited in the adipose tissue or the fat, okay? So in some studies, about 75% of consumers were extremely sensitive to that. All right, so that's a huge portion of people. I know I was, you definitely were. It's very, very common if we do actually consume that boar meat. And then another place that scadal comes from is in the colon of the boar. And so again, these hormones traveling through the bloodstream, they don't just go to one place. They don't just go to the hypothalamus or to the testes. They travel the whole body. And so in this case, they're triggering additional steroid productions from the colon, which again is depositing more of that steroid hormone in the liver and allowing it to be deposited into those fat cells of the adipose tissue. So now we're going to move into not necessarily a reproductive management product, but a tool. So we're going to talk a little bit about semen sexing and why we would do that. So one of the places that semen sexing is probably the most popular, or we use it the most, is in our dairy industries to get heifer calves. So as probably many of you know, bull calves are very undesirable in the dairy industry. They don't make us milk, and dairy calves are really not worth that much money. But if we can sex sort semen and get more replacement females, then we can help have more replacements in our group, making more milk and having hopefully more desirable females. Okay, the dairy industry has also gone really heavily to using a lot of beef on dairy semen to try to increase the profitability or desirability of their male offspring. And then they're using their most desirable females and breeding those with this sex sorted semen. Okay, so what's actually determining the sex of the embryo? So we have our genome, our bovine genome here, or genes. Okay, and there's 22 plus our X and Y's in the cow. And what actually is defining the difference in what sex that embryo is whether that sperm cell is X-bearing or Y-bearing. Okay? And then how we actually do this is we sort those X-bearing sperm from the Y-bearing sperm based on their amount of total DNA content. Okay? That's cool. That's legit science. And this is why I study male reproduction. This is cool. So yeah, the total DNA content is how we're actually able to sort those sperm cells. Okay? So how this actually works is we have our ejaculate, and we add it's a special dye to the sperm cells, and then it binds to the nucleus or the head of those sperm cells. And then we're going to look at the total DNA in our X versus our Y sperm cells. Our X sperm cells have about 3.5% more DNA. So yay for girls. A little bit more